Hi, today I will talk about edgeR and limma, and if you hear these names for first time you might think, what? Is it some sort of animals? No, it is about RNA-seq analysis, and whenever we talk about RNA-seq analysis, then we usually mention two types of protocols. One is edgeR and other is dseq. What limma and edgeR are, there are acronyms for the following. Limma is a sort of linear models and differential expression for microarrays. That's the name come from. And edgeR is short for empirical analysis of digital gene expression data in R. You can figure it out yourself if you check bioconductor front pages for limma and for edgeR. Scientists are very creative in inventing new names, and this is one example out of many. And you can read about RNA-seq analysis, which is easy as 1, 2, 3 with limma, glimma, and edgeR. Never mind glimma. Or there are some other papers, like limma about differential gene expression, issued in 2015, and edgeR dated in 2010. But if you think that edgeR came first and limma second, no, it isn't. You can check bioconductor page, then open limma users and see that the first edition of limma was in 2002. And then you go to edgeR page and you see that edgeR depends on limma. And if you go to the tutorial, you see that the first edition of edgeR is 2008. In other words, edgeR is actually built on the top of limma, and it's all coming from the same group of Gordon-Smith. If you think that limma is only about microarray data, no, it isn't. It's even in a title. It's a small part of the tutorial, you see, and if you come to this chapter, there are all nice words about limma and edgeR. They basically use the same concept, that empirical bias is in both, that limma trend is used, or WOM. WOM is now for RNA-seq data, not microarrays. And then they suggest some lines how to analyze RNA-seq data, and it feels like you copy-paste them into the script somewhere from here up to here. Then the core of the business will be done, and there is not much else to do. Let's copy-paste these lines into RStudio and check what else has to be added to make it working. Alright, that's my copy-paste of the lines from the limma. Of course, you realize that on its own it would not work at all, because you still have to define counts and you have to make a design of your experiment, which is based on the samples information. You need samples description. And of course you have to load library edgeR, and when you do it, you also import limma. You also import geoquery, because you will need it for sample information. Then I use example which I used before of this GEC number. This is the site. It is a long list of samples from aged and young individuals, all human, and some patients with diagnosed MDS. And counts are taken from this file. So we briefly define the directory where it is, we load the data. These are the data where there is some redundancy in gene names, therefore you cannot just declare it as raw names. You have to find a duplicated genes. So there are 2 duplicated genes only, not a big loss. Then we remove it, keep those which are not duplicated, then declare raw names, then delete this extra column. Now read counts table is ready. Okay, we still cannot run those lines because we need the sample information. As I told you before, the universal way of getting sample information is using getGeo function from GeoQuery. So you use the same number as for data, only this data are downloaded and this info you can fetch. So you do it exactly the same way as for microarrays. Now samples are fetched, it's a complex data. You have to go to phenodata, data, and then you see finally the information. So this address is okay, and you copy paste this line into here, and then it is your SAM, which is short for samples again. There are lots of column names in this smaller table. I would select the title, geoaccession, age, cell type, this and disease diagnostics. That's what we need for our model and differential expression. So then we make a smaller table out of it. There is a bit of problem that MDS samples have no age. Okay, let's continue. And then I say I use a function grep for MDS in row names, and then define the filter again, and then for this filter positions I say the age will be unknown, and then I also rename, simply copy paste and edit this line, simplify the titles a bit and make it a bit shorter. Yeah, that's the table with Ank. Note that this title are column names. You might think we got the data, we got the sample information, now we can proceed with analysis, but no, it's not yet done. We have to make sure that the order of the column names in the data table and in the sample table are the same, which is not the same. The columns are quite messed up in the original data file. What we do, we have to write this part extra to make an alignment, so to say, between call names data and samples title column. First we check are all column names in data are in the samples titles, and the answer is no, there is one which is not. It might be bookkeeping mistake, but we don't want to guess and correct the data, because if we are wrong, then the whole process is wrong. We remove this column by again using filter, saying that only those call names which are in the samples, and filter by this. Now we do the reverse and check are all the titles in a sample title column are in the call names data, and again it is not, one is false, and we filter it off, even though we think that those two positions are the same sample. We might hypothesize, but again I would not take it because it is still a hypothesis. And now in the last line we do the alignment by calling data as there are in a sample title order. We make them in the same order. So now the order of the columns is the same as in a sample. Now we declare DJ list. This is the first line out of the true HR core business, where we declare end counts and samples at the same time. And for the first time we can call the illustration the histogram. It is immediately log transformed +1 to avoid trouble with the zeros and low counts. And we see that original data table contains lots and lots of zeros, which will be next removed. And we also can check the sample information after the import by calling DJ samples. And again, the first column is the order of appearance of the samples in the data file, and the rest is coming from the sample file. And now you see that they are all perfectly aligned to one another. All the names are in the right places, and so we don't make any mistakes. We can also visualize how many read counts are in every sample and how many gene counts are in every sample. For read counts we take column sums all the read counts for each sample. For gene counts we do the same, only we use the true false table instead by declaring tell me what is above 0. If it is above, then it is true, and true has also numeric meaning of 1, and this why we can count how many genes are expressed. And now we plot them. Now we see that the lowest in the gene counts is MOS 6 and 11 and MDS 9954, and the rest is let's say higher, but keep it in mind. This line we did already. Now we're ready for design. And now for first time we do a filtering. Note that this is more or less the description out of tutorial. So you can compare this DJ list, filter by expression, keep only what is not filtered off, calculate normalizing factors, and then log CPM, fit, e-bias, and top table. We do design, we do the keep and DGA. Now we insert a box plot because we still like to see how the data look like before normalization. It's pretty variable, and again you see MOS 6, MOS 11 and a few others are leaning to the bottom of the plot. It is usually indication of low read counts, and indeed we know that these two are at the bottom of the read counts and gene counts. That's the explanation. Then we follow the protocol and calculate the normalizing factors, and we check that now we have a table of counts per million with normalizing factors added. And before we do a next box plot, we do a log transform, which is again a necessary operation. And now we check the box plot of normalized log transform data. This is what will be used for analysis. And again, those two samples are a bit of outliers, but we do not remove them because we take data as they are. At this stage, we can redo the read counts now for log CPMs and gene counts, and the plot and the text. And here you see that again, MOS 11, MOS 6, and MDS 19954 are even more extreme outliers out of the rest of the group. This is what you can keep in mind if you one day will think to remove those samples. The second note is about DJA sample table. Pay attention that lip size is mentioned also in a table, but it belongs to unfiltered data. It doesn't change when you filter them. Also, the column norm factors appear after normalization step, and by appearance of this column you can always conclude that normalization has happened. And now we plot MDS, and note that the colors are inherited by the trick saying as numeric as factor DJ samples and H column. So we simply use this H column, which is young H and unknown, as colors 1, 2, 3, blue, red, and green. And we see that young blue cloud is pretty compact and reasonably separated from red and green, which is either MDS or aged samples. So we have a good expectation of finding differential expressed genes between young and either MDS or old. But it would be not easy to find difference between MDS and aged, which is still possible. Now pay attention that unlike to the suggestion in the tutorial, we do fit differently. If in tutorial they say fit and then go to eBias and top table, I have 3 columns, so I have to put in between fit 2 and use a contrast matrix. That's what I do in addition. Then I'd like to see the cloud, and the cloud is a bit problematic, so there is a dispersion far away from the major cloud, so WOM might make sense for this data. Then I use a fit2 for the contrasts, and then I use decide test, which is a sitting in limma, why not? And now I see that if I compare aged and young, I have up and down genes, and I can extract names out of it and do my top table and tops. That's more or less the business with this data. There can be more illustrations, of course, but that's the bare minimum. If you expect some concluding remarks, here I have some. First, pay attention that public data almost always contains something unexpected. Spare your energy and use your creativity to circumvent those unexpected things. And do not criticize public data, because one day somebody will be in the same position with your data. Second, always check the steps in your script, and illustrations are very important for those checks. If you work without illustrations, you're literally blind. Don't do it. Then regarding tutorials and how it compares with your script, now you realize that the most of the script is not about major lines which are mentioned in the tutorial. You spend most of the time for decorative work or for adjustments of different parts of the data, and it needs your good knowledge and creativity, and there are many options for this, so find those which suits you the best. And while you're writing the script, keep the major line always in mind, so always make a plan in advance what you want to do in this particular script and what you don't want. That's more or less the story and the moral of it.